So today I'm going to be completing part B of homework 1 for process dynamics and controls. Now, I've already got our model here set up. We've got our two gravity drain tanks, each with a cross-sectional area of A with a drainage hole area of AO, with an initial flow rate Qin going into our first tank of H1, and Q out of Q1 going into our second tank that has an outlet flow rate of Q2. Now, from here, I'm going to pull out those differential equations we figured out in part A. So dH1 dt equals 1 over A times Qn minus Q1. And as we previously figured out, our Q1 is actually just our drainage hole area times the square root of 2g times H1 to the 1/2. So we can go ahead and sub that in. Say that 1 over A times Qn minus AO square root 2g H1 to the 1/2. And we can do the same exact thing for dH2 dt and say that it's equal to 1 over A times Q1 minus area of the drainage hole square root of 2g times H2 to the 1/2. I've already done all of this in our previous part. The point of this exercise is to try to get closer to our set point by using a proportional integral controller. And how are we going to do that? Well, we're going to take our original controller, our Qn equals Qn, our initial steady state, plus our proportional controller gain, Kc, times our error, which, if you remember, equals our HSP minus H2. And then we're going to add our integral portion. So we're going to add Ki, our integral controller gain, times the integral from 0 to t of the integral, our integral error, which is actually the same as our original error. It's just going to be HSP minus H2. We're going to do this with respect to tau. All right, now what are we going to do with this? Well, we need to apply the fundamental theorem of calculus to get this into a usable form. The fundamental theorem of calculus, which we're going to call FTC here, states that the derivative of the integral of a function is just the function itself. So we can say that d e int dt just equals HSP minus H2. And that allows us to simplify this equation a little bit, taking us to Qn equals our Qn at our initial steady state plus Kc times E plus Ki times E int. From here, we can find our governing equations for our proportional integral system, which are going to be dH1 dt equals 1 over A times Qn, which we're now going to sub in with this big equation right here. So our Qn at our initial steady state plus our proportional controller gain plus our integral controller gain. And we're going to subtract that with Q1. And for our second governing equation, we're going to get dH2 dt equals 1 over A times Q1 minus area of our drainage hole times the square root of 2GH2 to the 1/2. And from here, we can move on to the process simulation part of this. We can go into Python and see how this actually works. So we need our plot so we can get paid. Alrighty, I'm going to go ahead and begin the coding portion of homework 1, part B. So as you can see here, I went ahead and imported NumPy as NP. I've imported our solve IVP so that we can go ahead and solve our dynamical equations that we found up on the board there. And I've imported make subplots so that we can see a plot of how close we're going to get to that set point we have so that we can get paid. So first thing we're going to do is we're going to put all of our constants in here, all of our values. So starting out, of course, we've got the gravitational constant, which is 9.8 meters per second squared. And then we've got the cross-sectional area of our tanks, which is 1 meter squared. We got the cross-sectional area of our drainage hole, which is 0.1 meter squared. And then from here, we need to find our initial Qn, which we're going to call Qn naught, which is 1 meter cubed per second. And with our Qn, we're going to be able to find our initial height, which, as we figured out in the previous video, is our initial Qn over the area of our drainage hole, all squared divided by 2 times the gravitational constant. Alrighty, from there we can find our HSP, our set point, which is going to be 1.2 times our initial height, as our set point height is going to be 20% higher than our initial height. From there, we're going to go ahead and put all of our controller gains in here, the first one being our proportional controller gain, which for now we'll call 0.1. And then, of course, we're going to have our integral controller gain so that we can make our integral controller, which we're going to call 0.03 for now. Man, struggling today with the typing. Then from here, we're going to set our endpoint for our time plot, which we'll just do 1,000 seconds for now. And then we're going to need to create the space for our t-plot. So to do that, we're going to do t-plot equals np dot linspace. Oh, look, the AI's got it for me. And we're going to go from 0 to our endpoint with 1,000 points in between. And from here, just to verify that we've got everything all right, I am going to check what our H naught and our H set point is. That looks all good to me. All right, now that we've got our variables in here, we can start to do some defining. First thing we're going to do is create our alpha value, as we had in the first video, which is going to be equal to the area of our hole times the square root of 2 times g. Now, it's important that we put this in here because we need to put this little function here into a lot of our equations that are going to follow this. So this just makes everything a little bit easier. So now we can go ahead and define our right-hand side as a function of t and our vector. And of course, our vector is going to be our h1, our h2, and our integral of our error, which we're going to call e-int. From here, we can go ahead and find our Q1 and our Q2, which are going to be equal to our alpha times the square root each of our respective heights. So go ahead and do that for Q2 as well. And that's all good. And then we need to define our error, which as always is going to be our set point minus our H2. And with all this information, we can finally put in our controller. So our Qn is going to equal, as we derived up on the board, our Qn not plus our proportional controller gain times our error plus our integral controller gain times the integral of our error. And then from here, we need to return our Qn minus our Q1 over A, our Q1 minus our Q2 over A, and of course our error. Now that we have defined our right-hand side, we can go ahead and finally solve our initial value problem. To do that, we're going to say our result equals solve IVP. AI is really just cheating for me here, but we'll go ahead and talk through what each of these are. We need to put down our right-hand side, our independent variable, which is going to be our time, so 0 to t end. Of course, our right-hand side is our dependent variable. And then we need to put in our initial values, which for our time is going to be, or for our height is going to be h naught for both tanks. So h naught, and then 0 to start for our time. And then from there, we need to put in our method, which, again, do the Radal method. And we need our dense output to be true, since we are dealing with continuous data here. And now that we've got a result defined, we can define our H1 plot, our H2 plot, and our integral error plot. As the solution based on our t-plot. All right, so it's finally time. We've solved our IVP. It's time to make our plot and get our pay. So to do that, we're going to say our figure equals make subplots. So we can go ahead and put our little plot into the universe. And to this, we're going to add our H1 values. We're going to figure dot add scatter. We're going to set our x values equal to our t-plot, our y values equal to our H1 plot. We're going to do mode equal lines, so it's nice and pretty. And finally, we're going to name this plot H1. And then we're going to do the same for our H2 values. AI is really doing me an assist here. So H2 plot, mode equals lines yet again. And we're going to go ahead and name this one H2. Finally, we're going to update the layout of our plot. And we're going to set our width equal to 600, our height equal to 400, and we're going to have our template be flatly dark, so it's nice and pretty. Alrighty, let's see if that worked. Go ahead and run all. One tiny little error there. Alrighty, and look at that. Beautiful. So are we converging on our value? It looks like it's just to check that again. Let's go for 100,000 seconds. Computing is cheap. Let's see how close we can get. Look at that. We perfectly converge on our set point. So our integral controller worked, and you can see it simulated here.